Hi, and welcome to BubbleNet, a deep learning framework for predicting the physics of bubble flows. To begin with, bubble dynamics is widely observed and applied to chemical physics, medicine, biology, etc. Here we propose four examples of bubbly flows. The first is bubbly flow generated by experiments, which are applied to manufacturing, petroleum engineering, machinery, etc. While the second example is the flow of red blood cells, where there are two different fluids within and outside the cells, which can be viewed as multiple microbubbles separated by biomembrane. The third is a drug delivery process in medical operations, where there are drugs contained in microbubbles, and the microbubbles are stimulated by ultrasound, causing the drug within to be released. Well, the last one is the application of the blood-brain barrier opening for curing brain diseases, where microbubbles are injected into brain vessels and stimulated by ultrasound, similar to the last case. While seeing these examples, we know that bubble dynamics are mainly applied to biomechanics and medicine. Now, we will introduce one of the most popular deep learning framework proposed in 2018, the Physics-Informed Neural Network, or PINN. So PIN consists of two main parts: the traditional deep neural network with input, hidden, and output layers. The input layers are the space-time domain fields of the physics model, namely x, y, z, t for three-dimensional models. The output layers consist of the physics field contained in the governing partial differential equations, or PDEs, such as velocities, pressures, etc. PIN also has a physics-informed part, using automatic differentiation to embed the governing PDEs into the loss function, obtaining the data from the physics field of the output layer, so that the neural network can approximate the real physics during training due to the physics equations are encoded into the loss function. Now, we will introduce our work using physics-informed deep learning to predict bubbly flows. We set up two cases of bubble flow. Both have biomedical backgrounds. The first one is a single bubble flow, similar to bubble flow of the blood-brain barrier. So here we set up a 2D microtube with length of 15 micrometers and diameters of 5 micrometers. We set up a microbubble of diameters of 4 micrometers, similar to the scale of cells and microbubbles in the vessels. We give periodic boundary conditions of pressure difference of 10 pascals. There are two pressure constraint points at the end of the tube with pressure of 799.932 pascals, equals to the pressure of human interstitial fluids. The initial condition is set up to be a constant pressure of 799.932 pascals, and the numerical simulation of the single bubble flow is shown right here in the right, running for 5,000 microseconds. While similar with a single bubble simulation, we set up a 2D microtube with length of 100 micrometers and a diameters of 50 micrometers. We set up 60 microbubbles of diameters of 3 micrometers, randomly distributed in the microtube. The initial conditions and boundary conditions are the same with the last case, and the simulation results is shown in the right, running for 3,000 microseconds. While to ensure the simulations are carried out correctly, we here test the liquid-gas ratio during the whole simulation to ensure that the component variations are within the acceptable errors. Here the red dotted line is a theoretical component ratio and the blue line is our simulation results. In the simulation, we adopt the time-dependent level set algorithm, where the computation follows the Navier-Stokes equation, taking the form partial phi partial t plus gradients phi dot velocity u equals 0. Here phi is a level set phase function, varies between 0 and 1 across the free surface, and is constant at 0 or 1 in the bulk of the two fluids. The density and viscosity of different fluids follows rho equals rho 1 plus phi times rho 2 minus rho 1, and mu also follows the equation. And for the level set algorithm specifically, the interface is described by the following equations, where gamma is a reinitialization parameter, which equals 1 in our case, And the epsilon level set, or epsilon ls, is a parameter controlling the interface thickness, equals 0.43 in our cases. Now, based on pre-mentioned PINN, we proposed our deep learning or deep neural network for predicting bubbly flow, the BubbleNet. So BubbleNet entails three main parts. One, deep neural networks, DNN, with subnets for predicting different physics fields. Here, we apply 30 neurons times 9 layers deep neural net for each subnet. 2, the physics-informed part, with the fluid continuum condition encoded within. And 3, the time discretized normalizer, or TDN, an algorithm to normalize field data per time step before the training. We train our simulations data of the two bubbly flow on BubbleNet. The loss function iterations diagrams are shown right here. We trained BubbleNet to predict the 4 physics field, the level set phase function phi, velocities in the two directions u and v, the pressure p. Here shows the phase function phi for single bubble flow and the multiple bubbles flow. The velocity in x direction u for single bubble flow and the multiple bubbles flow. The velocity in y direction v for single bubble flow and the multiple bubbles flow. The pressure field P for single bubble flow and the multiple bubbles flow. We can also estimate the errors between our CFD benchmarks and our predictions. Here shows the absolute errors for phase function phi for the two simulation cases. The absolute errors for velocity u for the two simulation cases. Also, absolute errors for velocity v for the two simulation cases. And eventually, the absolute errors for pressure p for the two simulation cases. That's all. Thanks for listening. The details about this project can be viewed at hanfengjai.net/bubblenet. The code can also be downloaded through GitHub at the link. If you have any further questions, feel free to email me at the following email.